As an excellent tradition of the conference, the 2000 IEEE International Robotics and Automation Conference Committee publishes the video Proceedings covering new and significant experimental results, demonstrations, and industrial case studies in robotics and automation. The purpose is to enhance and complement the results presented in technical sessions and published in CD-ROMs. Authors' abstracts and references accompany this videotape. This year's video Proceedings of research from around the world includes 26 segments categorized into the following groups: mobile robots, human-machine coordination and human-centered robotics, virtual robotics and virtual factories, manufacturing automation, Robosen 3 compact wall climbing robot, Spain.
Robosen is a family of 3 pneumatic wall-climbing robots designed for inspection in nuclear power plants. The robot shown in this video is the 3rd member of this family, designed for the inspection of radioactive cylindrical tanks. Here we see the robot climbing on a vertical tank wall. With a novel locomotive mechanism, it is able to climb vertical walls at speeds around 0.1 meters per second. Robosen 3 is a compact pneumatic robot of only 3 kilograms. It is composed of an aluminium body which accommodates electro valves, sensors, cameras, and part of the control electronics. The robot climbs using 4 suction pads as legs, which are moved by pneumatic actuators. The vacuum is generated inside each suction pad by Venturi effect. An umbilical cord links the robot to the control station to provide compressed air, electrical power, and communications. In addition, water is provided when measurements are being carried out, to guarantee good contact between the ultrasound sensor and the tank wall. Each suction cap has a vacuum sensor whose measurement is used by the control algorithm to establish whether a step is successful or not. If a step is considered unsuccessful, it is repeated with successively shorter strokes until sufficient vacuum is achieved. This simple strategy allows the robot to pass over welded joints found in steel tanks without compromising the robot's safety. The control station is composed of a navigation monitor, suction pad, the motion controls, and the onboard camera views. The distinctive features of Robosen 3 are the simplicity of its mechanical design and the compact and robust nature of the independent vacuum generators inside each suction cup.
Inflatable rover demonstration, USA.
My name is Jack Jones, and I'm the task manager for a novel planetary robotic research program known as the Inflatable Rover. The primary application for this vehicle is the surface of Mars, where it should be capable of traversing over 99% of the rocky surface simply by going over the rocks instead of around the rocks. The rover can be delivered to the surface of Mars by any of a number of means, including, as shown here, a solar-heated hot air balloon known as a solar montgolfier. This balloon, which has a hole designed in the bottom, fills itself with air while falling and is quickly heated by the sun. The partially buoyant balloon can gently land the rover with the inflated wheels acting as airbags. The balloon can then go on to provide its own exciting imaging and science mission for the remainder of the day. Meanwhile, on the Martian surface, the rover will extend its chassis and inflatable solar array and become fully deployed. It can travel equally well in forward and reverse while performing intricate science measurements on the Martian rocks and soil and looking for possible evidence of past or present life. The prototype rover we've actually built would be capable of traveling on the Martian surface at a moderate walk of 3 miles per hour or 5,000 meters per hour while consuming less than 20 watts of power. It presently weighs only 20 kilograms or 44 pounds, but yet it is as large as some sport utility vehicles. We've also tested it in very rocky canyons, characteristic of some of the most rugged terrains on Mars. The rover easily climbs over boulders that are over 1/3 the diameter of the wheels. And we've accumulated many miles of operation without a single puncture in the tires. On Mars, though, we would provide our own miniature tire pumps, along with wheels that are more rugged than the commercial nylon balloons we are using as tires here. And finally, we tested the inflatable rover's ability to travel on calm lakes, similar to the liquid methane lakes that are anticipated on Saturn's moon Titan. We are hoping the inflatable rover will provide a faster, better, cheaper means to visit the various solar system planetary bodies. And it may someday leave conventional rovers in the dust.
A robotic reconnaissance and surveillance team, USA.
A consortium headed by the University of Minnesota, including MTS Systems Corporation, Architect Honeywell Incorporated, has developed a novel two-tiered heterogeneous multi-robot system for surveillance and exploration tasks. At the first tier of this team is the Scout. Scouts are small, mobile sensor platforms used in a cooperating group. At the second tier is the Ranger. Rangers are larger robots used to transport, deploy, and coordinate. Scouts are wholly original robots with cylindrical bodies 40 millimeters in diameter and 110 millimeters in length. The Scout carries a sensor payload used to relay environmental information to other robots. The most common Scout payload is a small video camera, but other payloads, such as microphones, are also used. Video data is broadcast to other systems via an analog RF transmitter. Scouts communicate with other robots using an RF data link. One specialized Scout has a camera mounted in a custom pan-tilt unit, allowing the robot to view its surroundings independently of the orientation of its body. The Scout has two modes of locomotion to allow it to navigate different kinds of terrain and obstacles. The first mode uses its wheels, allowing it to drive over smooth surfaces. Here, the Scout demonstrates its ability to climb a 20-degree slope. The second mode of locomotion is the hop. The hop is accomplished by winching the Scout's spring foot up around its body and then releasing it suddenly. Here, the Scout jumps over an obstacle. Scouts are deployed by Rangers. The Ranger is a modified commercial all-terrain robot. The Ranger uses a launcher to deploy Scouts into the area in which they will operate. A Ranger can carry and shoot up to 10 Scouts from its launcher. Rangers supervise the Scouts while working with other Rangers. Rangers report to a human group leader. The Scouts are designed to withstand the impact of landing and of being shot into and through obstacles, such as these simulated windows. The Scout's small size, its deployability through launching, and its multiple locomotion modes and sensor payloads give it the ability to explore difficult-to-reach areas and report useful data. Combining the Scouts with Rangers, which provide the ability to travel longer distances and to have greater computational resources, forms a useful reconnaissance and surveillance team.
An innovative space rover with extended climbing abilities. Switzerland.
Autonomous mobile robots have become a key technology for unmanned planetary missions. To cope with the rough terrain encountered on most of the planets of interest, new locomotion concepts for rovers and micro-rovers have to be developed and investigated. In this video sequence, we present an innovative off-road rover able to passively overcome unstructured obstacles of up to 2 times its wheel diameter. Using a rhombus configuration, this rover has 1 wheel mounted on a fork in the front, 1 wheel in the rear, and 2 bogies on each side. Here we can see the trajectory of the front wheel mounted on the fork. An instantaneous center of rotation situated under the wheel axis is helpful to get on obstacles. To ensure good adaptability of the bogie, it's necessary to set the pivot as low as possible whilst simultaneously maintaining maximum ground clearance. This architecture provides a non-hyperstatic configuration allowing the bogie to adapt passively to the terrain profile. Motion in structured environments. For climbing stairs, it's necessary to have a good correlation between bogie size and step dimensions. We can see that the rover is able to climb regular stairs effortlessly. Motion in an unstructured environment. We also made some outdoor tests on rocky terrain. As can be seen, the rover demonstrates excellent stability on rough terrain. It advances despite a lateral or frontal inclination of 40 degrees and is able to overcome obstacles like rocks, even with a single bogie. In a next step, the robot will be equipped with adequate sensors for fully autonomous operation.
Marsupial robot teams. USA.
This video presents ongoing work at the University of South Florida with a new team of robots called marsupial robots. The term marsupial is derived from the way a larger robot can transport and provide distributed processing and control of one or more smaller robots, much like a kangaroo mother carrying a joey in her pouch. Battery-powered Jeep. It has an onboard computer and a full complement of navigation and mission-specific sensors, including 2 cameras, thermal sensing, sonar, inclinometers, and GPS. The robot is a commercially available shape-shifting robot with a camera and lights. All power and processing is supplied by the mother through the tether or umbilical cord. The USF marsupial team was originally designed for urban search and rescue, where the robot team cooperates to autonomously search for survivors of an earthquake. For example, the mother is too large to enter this room and cannot fully explore it from outside. The daughter is small. Battery power and computational processing are supplied by the mother robot, making small rovers more practical in the field. The marsupial approach is also useful for military missions and planetary exploration. Marsupial teams involve the entire spectrum of distributed cooperative control. They also rely on advances in single robot control. In this docking demonstration, the daughter is using a low-complexity vision algorithm to home in on the colored landmark, much as a bee homes in on its hive. Marsupial teams pose many open research questions in control, distributed artificial intelligence, and distributed sensing. In winter of 2000, we will extend the marsupial team to include 3 untethered robots as daughters, increasing the challenges of intelligent cooperation in teams of heterogeneous robots.
Polybot. Demonstrations of a modular, reconfigurable robot. USA.
The idea behind modular reconfigurable robotics is to build up complex robots with many modules that are mostly identical, each one containing actuation, sensing, and computation. The modular, mostly homogeneous nature of the system allows it to be reconfigurable. This simulation, made in 1994, shows when reconfiguring would be beneficial. The first part shows the robot using a rolling track mode of locomotion, which is the most efficient gait over flat terrain. The earthworm or snake-like gait turns out to be the best for crossing obstacles, climbing under or through things, or going over large steps, and so on. Finally, the last area is grassy, bumpy, and uncertain. The spider configuration is the most stable for crossing uncertain terrain. At the time this simulation was made, the spider gate had not been implemented. Here, 32 modules use the rolling track gate down a long hallway. This is the first instance of a robot system reconfiguring to use 2 topologically different modes of locomotion. One advantage of these systems is that they are very versatile. They can easily be reconfigured into a large number of configurations. The system can manipulate objects individually, one arm at a time, or in a distributed fashion. The duality between locomotion and manipulation is demonstrated here, as the same gate used for manipulation results in locomotion. One application for these systems is search and rescue in a rubble pile. Here, a pile of debris has been dragged into the lab as a test environment. Crawling through pipes or rubble would be useful in searching for victims in an earthquake-damaged building. Once a victim is found, the system may reconfigure into some sort of supporting structure. This research is partially funded by DARPA, a U.S. defense agency. Here, U.S. Marines have set up a test obstacle course for this early prototype of Polybot. The system successfully navigated through most of these obstacles. In addition to navigating up and down ramps, steps, and ladders, Polybot had to overcome obstacles like crawling through pipes, over loose debris, monkey bars, and chicken wire. These next-generation modules have computation on board. A Motorola PowerPC 555 is on each module with 1 megabyte of RAM. They can also go 10 times as fast as their predecessor. They communicate with each other over a CAN bus. High-level commands are sent by a human to this 9 degree of freedom snake over this CAN bus. Power is supplied off-board. Integrated environmental sensing on board, and the system will be able to reconfigure itself automatically.
High-speed navigation using the Global Dynamic Window Approach. USA.
The Global Dynamic Window approach presented in this video allows mobile robots to navigate robustly and at high velocities in dynamic and unknown environments. The map shown in the lower left corner of the screen shows obstacles as perceived by the robot. The path of the robot is traced in red. In each of the presented experiments, the robot initially has no map of the world. Some of the obstacles shown here are not visible from the robot's location through this blocked passage to this goal location. The shaded area in the map represents the navigation function that is updated in real time. From the robot's initial position, the blocked passage appeared to be open. As the robot discovers that the passage is blocked, it circumnavigates the obstacles to reach the goal position. This behavior is achieved simply by specifying a goal location relative to the robot's initial position. In this experiment, the robot will move autonomously for 40 meters at a velocity of 1 meter per second. A goal position relative to its current position is the only input to the algorithm. Initially, the robot has no map of the world. Using sensory information from a SICK laser rangefinder, a world model is built. Given the goal location and the current world model, a navigation function is computed in real time. The gradient of this navigation function serves as a guide to the goal. In choosing the motion commands, the dynamic properties of the robot are taken into account. The guidance by the navigation function and the selection of dynamically sound motion commands lead to extremely robust and fast motion. The video shows the robot moving at its actual velocity. The bending of the path in the upper part of the map was caused by slippage of the wheels. The final segment of this video demonstrates the global dynamic window approach in a dynamic environment. The robot successfully circumnavigates two groups of robotics researchers that step into its path. Despite their efforts, it safely reaches its goal location.
New type leg-wheel hybrid vehicle, Japan.
Rollerwalker is a new type of leg and wheeled hybrid vehicle. Conventional vehicles have used driven wheels, which consist of driving actuators as well as steering and braking mechanisms. This not only makes the leg mechanism extremely heavy and bulky, but also restricts the versatility of the leg movement. On the contrary, Rollerwalker utilizes passive wheels. On rugged terrain, Rollerwalker makes normal walking motion. On smooth terrain, it transforms into its skating mode. The propulsion is the same as roller skating.
Remote gaze control of a camera from human eye movements, France.
A video camera, placed at a given location on a turret that allows it to pan and tilt, captures an analogical image sequence. The video signal is transmitted toward a coder that transforms and compresses the signal into digital data. The data can be routed via a telecommunication network to a second location, even very far away from the first location. The data is then decoded and viewed by an operator. The latter watches the image through a semi-reflective mirror that lets a small camera observe the operator's eye movements. The operator can direct and focus the camera in real time on a point of interest using eye movements. The goal is to control the movements of the camera in such a way that the region of interest always remains within the field of vision of the operator. The movements of the eye are analyzed by a computer next to the operator. The data resulting from this analysis is then sent by serial link to the coder, routed by the telecommunication network, then decoded and again transmitted by serial link to another computer located next to the camera. The second computer drives the movements of the camera. To analyze eye movements, a semi-reflective mirror lit by two infrared diodes is used to let a small camera observe the operator's eye, while letting the operator watch the video screen. Remotely following and monitoring the movements of a robot in a hostile or difficult-to-access industrial site is an example of application of remote camera control by the eye. These results can also be. The idea is to keep a good reconstruction only in the zone of interest in order to increase the image compression rate for real-time transmission over telecommunication networks.
Mobile robot helper, Mr. Helper. Japan.
The system has been developed by Kosuge Laboratory at Tohoku University in cooperation with Omron Corporation, Japan. Mr. Helper has been developed for enabling a human to manipulate a large and/or heavy object without any human helpers. Mr. Helper consists of two manipulators and an omnidirectional mobile base, and is equipped with a wrist force torque sensor. The omnidirectional mobile base is driven by 4 rate-controlled DC motors through the button mechanism developed by Hirose Laboratory at Tokyo Institute. Mr. Helper also has a stereo camera system on the tap for the future experiments. In this system, a human and Mr. Helper communicate to each other by intentional force. That is, a human manipulates an object by applying intentional force and torque to the object. To realize stable object handling by the human and the robot, we designed an impedance-based control system. An impedance controller for each manipulator was designed so that the object manipulated by both arms has a specified impedance around a specified compliance center. The mobile base is damping controlled so that it has a specified damping characteristics around the center of the mobile base. The resultant passive dynamics guarantees the stability of the resultant system. We realized 2 types of cooperative object manipulations. In this picture, the robot helper supports the weight of the object, and the human only applies the intentional force. The next picture shows the load sharing between the robot and the human. The human and the robot support the weight together. The object to manipulate it. The load sharing is realized by the cooperative lifting up mechanism of the object. That is, the wrist angles of both manipulators generated by the human's lifting up motion are utilized to realize the cooperative lifting up of the object. When the human lifts up the object, the force and the moment are applied to the wrists of both manipulators, and the wrists of both manipulators rotate. Both manipulators are controlled so that the wrist angles generated by the human's motion converges to their initial angles. This video introduced the mobile robot helper referred to as Mr. Helper. Advanced robot-human interface will be implemented in the future.
Distributed mobile robot helpers, Dr. Helpers. Japan.
Helpers are multiple autonomous mobile robots developed for enabling a human to move a heavy and large object without any other human assistance. How the Dr. Helpers will assist a human to handle an object will be shown in this video. Dr. Helper consists of an omnidirectional mobile base, a forklift system, and a body force sensor. The body force sensor is a torque force sensor installed between the mobile base and the forklift system. Dr. Helper is autonomous and controlled by the onboard servo system and the onboard robot controller with a power supply from the onboard battery. Dr. Helpers communicate with a human by intentional force detected by the body force sensor. That is, a human applies the intentional force and moment to the object and transports it to the destination together with the robots. Let us consider the case where we'd like to move a chair with casters. The casters rotate to the direction of the intentional force applied by a human, and the human could move the chair to this direction. We will apply this principle to the control of Dr. Helpers. That is, each robot is controlled as if it has a caster-like mechanism. The passivity of the virtual caster dynamics guarantees the stability of the resultant system, including a human. The apparent dynamics of the object, supported by multiple Dr. Helpers, is affected by a caster offset of each robot. Larger offset will stabilize the straight line motion of the object against disturbances, but it will make the motion direction change difficult. The adaptive del caster action system is implemented in Dr. Helpers to adjust the offsets of the virtual caster according to the velocity of the object. With the adaptive del caster action, a human could transport the object easily. When the object reaches to the vicinity of destination, the human decreases the object velocity to position it precisely. In this case, the offset of the virtual caster becomes small according to the decrease of the object speed, and the caster rotates to the direction of the intentional force almost instantaneously. Only directional motion is thus realized for this case, and the human can easily adjust the position and orientation of the distributed robot helpers. Dr. Helpers have been proposed to enable a human to manipulate a heavy and large object by the human without any other human assistance. The distributed robot helpers will be applied to other tasks in future experiments.
Visual telepresence by remote control of an active vision system.
Described in this video enables the control of an Activision system by a remote operator using a virtual reality headgear. Both the head-mounted display and the Activision system are connected by a 100 megabit Ethernet local network. This kind of system can be used as a surveillance application. A remote operator can inspect remote areas by making the same movements that he would make if he were there. Since two images are being captured by the Activision system over the network to the head-mounted display, the operator can have the perception of 3D, being able to distinguish the relative depth of every object on the scene. By using a common filter, the system is able to predict the movement of the operator and compensate. 3 degrees of freedom are controlled by the system: pan, tilt, and swing. In this monitor, we can see overlap both images captured by the Activision system. The disparity shown is the one responsible for the 3D perception in the head-mounted display. The system tries to automatically adjust the versions of both cameras in order to maintain the 3D perception of the object in the center of the image. The operator can also manually adjust the versions using a joystick.
Telesurgery system for intravascular neurosurgery, Japan.
In the intravascular neurosurgery, a doctor inserts a catheter into blood vessel system from the femoral artery and navigates a catheter far deep into the cerebral artery. When the catheter tip is reached to the aneurysm is stuffed with very thin platinum coils. This new treatment has many benefits such as minimal invasion, early rehabilitation, and so on. But the exposure to X-ray radiation for doctors during an operation and the difficulty to operate a catheter inside the narrow cranial vessels cause a lack of well-skilled doctors. A solution for these problems is a telesurgery system. The catheter derivation system consists of a master joystick, which has very small mechanical impedance, and a slave device that follows the master movement well. The master-slave system has 2 degrees of freedom. The catheter is inserted into the blood vessels, and the treatment is performed. Each joint of the master joystick is connected to a DC motor by a wire. This mechanism realizes smooth motion and fine force display. Handle a catheter. An inner unit is dehanged by a set of thin beams from the outer shell. There is a pair of rollers which clutches a catheter in the inner unit. When the catheter side is contacted with the blood vessel wall, a strain gauge force sensor in the slave device measures the contact force. A microforce sensor is installed in the force which is generated between the catheter tip and the blood vessel wall. The diameter of the microforce sensor is 1.2 mm and resolution is 0.5 millinewton. This force information is displayed on the master joystick. The operator can easily understand what situation is happened in the blood vessels. An experiment of a catheter teleoperation is performed in the medical operating room. A doctor is able to control a catheter using the master-slave system in the same level as the usual surgery. He isn't exposed to X-ray radiation all the time during the experiment.
Twin-frame walking robots Parawalker 2, which had reduced DOF practical walking robot, Japan.
This is twin-frame walking robot Parawalker 2. Parawalker 2 consists of 2 frames with 3 legs. Each frame is connected by a 6-degree of freedom mechanism named SP Hybrid Platform. All legs can be grounded, and Parawalker 2 can walk on uneven terrain, maintaining stability because of these structural advantages. Parawalker 2 can climb upstairs. During this climbing motion, one leg attached to the upper frame is extended. Because we are using only one extendable leg, the weight increase is very small. Parawalker 2 is able to achieve enough stability on large-scale uneven terrain. From the results, one can observe that Parawalker 2 is a practical walking robot with reduced degrees of freedom. Parawalker 2 can perform the force control without extra force sensors. This controls the force toward the direction of gravity. Our force control system can select the control direction and axes. Next, this is the force control for the roll, pitch, and yaw axes. The 6 degree of freedom mechanism, SP hybrid platform, can measure its position and posture deviations. Parawalker 2 can perform various tasks. This grinding task is one of the practical applications. In this case, the lower frame has 6 degrees of freedom relative to the upper frame, so the lower frame acts as a 6 degree of freedom manipulator. Parawalker 2 can be used as a walking manipulator and moving platform for supporting other tasks. Parawalker 2 is a practical walking and task-performing robot.
The Robot Sheepdog Project, USA.
Flock animals such as sheep or these ducks can be moved as a group from place to place. You can see here how the ducks move almost as a unit. They walk and turn very closely together as they try to avoid contact with an apparent predator, in this case a human. This behavior is exploited by sheepdogs to control the movement of flocks. We have demonstrated a simplified version of the sheepdog's task using this robot to control a flock of real ducks. In this overhead camera view, our robot is interacting with the flock. Our goal is to hold the flock at a specific position at the edge of the arena. We created a simulation of the flock and used this to design a robot controller. The robot guides the flock towards the goal position at the bottom of the screen in this example, and then moves away. This is intended to reduce the stress on the real animals. The same controller runs here in the real world. The robot starts off at the goal position at the bottom of the screen and moves towards the flock. It moves around behind the flock, pushing them towards the goal position. The robot detects when the flock gets near the goal and begins to move away. The ducks have now settled very close to the goal position. The system will now stabilize with the ducks at the goal and the robot on the far side of the arena. This is the first demonstration of robot control of animal behavior, and because our robot was carefully designed in simulation, we avoided the need for repeated experiments with the animals. In fact, we were delighted to find that it worked the first time we tried it. This work was performed by Richard Vaughan and his colleagues at Silso Research Institute in association with the Universities of Oxford, Bristol and Leeds.
The platform for micro-positioning with piezo legs, Yugoslavia.
A platform for micro-positioning actuated by 3 piezo legs is presented in this video. The platform carries on board its control electronics, including a microcontroller. The motion parameters, direction and speed, are imposed with an analog joystick. On the top of the platform, there is a board for carrying the object to be positioned. To improve the contact between the legs and the ground, small steel balls were glued to the end of each tube. The 3 piezo legs are mounted in a way to ensure a parallel position of the corresponding electrodes. By polarizing electrode with a ramp signal relative to the internal common electrode, the leg bends slowly. At the end of the cycle, the leg stretches quickly. At this stage of the development, the platform is connected with 5 wires to the power supply and the PC. When legs bend slowly, the contact with the ground is preserved and the platform body moves to the left. During the quick stretching phase, the tips of the legs slip over the ground surface and the platform moves for a small increment. Repetition of this procedure results in a quasi-continuous motion. To enable the visual tracking of the platform motion, a glass plate with a fine grid is placed on it. The platform motion is monitored by a microscope. The grid on the glass plate is clearly visible. The platform can move in any direction. Using large steps of about 10 micrometers at high repeating frequency of 60 Hz, the platform moves at a quite high speed. To demonstrate motion stability and capability to realize the motion in the desired direction, the motion along the coordinate axis is also shown. Decreasing the steps to 0.5 micrometers at low frequency of 20 Hz, the platform moves very slowly. Even step-by-step mode is possible. As an example of a complex planar motion, rotation around the perpendicular axis, located far outside the visible area, is presented. The rotation is justified by monitoring the inclination and translation of the grid. Because the angular velocity is quite small, this part of the film was accelerated 4 times. Another mode of operation is with the legs stretching upwards. A glass plate carrying the object moves on the tips of the legs.
Architecture for Agile Assembly, Cooperative Precision Assembly, USA.
In the Microdynamic Systems Laboratory at Carnegie Mellon University, we are developing an architecture for Agile assembly which enables the rapid design, simulation, deployment, and operation of modular automated assembly systems performing multi-agent cooperative precision assembly. Minifactory, an example of the architecture for Agile assembly, is a community of 2 degree of freedom robotic agents cooperating to perform a precision 4 degree of freedom assembly task. A factory designer can use a web browser to contact an agent's computer and download its specifications directly into the AAA interface tool. An agent's self-description contains models and constraints which allow the user to quickly snap together the chosen components into factories within the virtual environment of the interface tool. There is no overall factory program. Rather, each agent in the factory has its own program, and the behavior of the factory as a whole arises out of the distributed interaction of the agents with each other and with the products flowing through the factory. The interface tool allows the development of agent programs in simulation, providing a 3D rendering of virtual factory operations as well as control panels to indicate the status of individual simulated agents. The agents are designed to quickly connect to the factory infrastructure with few or no tools. A single plug-in cable provides an agent with air, vacuum, power, and network services. The same programs developed in simulation run on the actual factory, even though no special care was given to precisely building the physical factory to match the virtual factory. The agents have the ability to explore their environment and to precisely calibrate the actual geometry of the factory. The same interface tool that was used to design and simulate the factory oversees its self-calibration. As the agents explore their environment, the interface tool updates its representation of the factory. When the exploration is complete, the virtual representation is precisely registered with the physical factory. The agents proceed with their distributed cooperative programs developed in simulation. They interact to assemble the product without any need for a central controller or database. The overhead manipulator agent is responsible for lifting and rotating parts, while the courier agents are responsible for transporting and manipulating parts in the plane of the factory floor. In this task, the parts, which measure just millimeters across, are aligned with assistance from computer vision to precisions of roughly 20 microns. The interface tool is still active during factory operation, providing a 3D rendering of the ongoing factory state and assembly progress. While we have presented a small example of a cooperative assembly task, AAA is designed to scale to much more complex assembly tasks, such as this factory, which is assembling small medical devices. The ultimate goal of AAA is to provide tools and mechanisms to rapidly deploy and reconfigure such automated assembly systems.
Force feedback teleoperation of a mini excavator over the Internet using a virtual master environment, Canada.
Virtual environments have been designed and implemented for training purposes and have been used as predictive displays to cope with the effects of time delays in teleoperation. At the University of British Columbia, we have successfully teleoperated a mini excavator over the Internet using predictive graphical and haptic displays. The teleoperated mini excavator is a Takeuchi machine that has been instrumented with joint angle resolvers, load cells and hydraulic pressure sensors. In addition, the machine pilot valve and control systems have been modified for computer control of the bucket tip position and impedance in task space coordinates. At the operator site, the user controls the excavator bucket trajectory by interacting with a real-time dynamic simulation of the mini excavator and its environment. This virtual environment provides the operator with both visual and kinesthetic feedback. The operator's hand position and forces are forwarded to the remote mini excavator via an internet link, where a local impedance controller combines the operator commands and local sensory information. Compressed video images of the mini excavator were also transmitted from the slave site to the operator via the internet link. The virtual environment is in turn updated based upon the mini excavator's bucket position and force measurements. This system was tested for the first time at the 1998 IRIS Pre-Con conference held in downtown Vancouver, where the mini excavator, located approximately 10 kilometers away at the University of British Columbia, was controlled by conference delegates. Despite a low data transmission rate of approximately 5 samples per second, the system remained stable, producing satisfactory tracking performance. The force position measurements have shown that the virtual excavator faithfully follows the commanded position in free motion with less than a 3% error, and the commanded force profile during contact with up to 20% in error. This system has applications in areas such as mining, forestry, and waste handling and disposal. In the future, the physical environment model parameters will be identified and used online to update the virtual environment model at the master site. This will help to reduce force tracking errors.
RRT Connect, an efficient approach to single query path planning, USA.
This video demonstrates a randomized algorithm for solving single query path planning problems in high-dimensional configuration spaces. The method works by incrementally building 2 rapidly exploring random trees rooted at the start and goal configurations. The trees explore space around them and advance towards each other through the use of a simple greedy heuristic. A 2D environment is used for testing and for understanding how the path smoothing optimizes the initial random path. This example involves an elbow-shaped rigid object that translates and rotates. This planner is suitable for single query problems since it involves no pre-processing of the environment and operates by randomly sampling the configuration space. This example involves a detailed 3D model of a grand piano moving in a room with walls and low obstacles. Several tricky rotations are required in order to solve this query. This example involves a Puma 560 industrial manipulator. The Puma has 6 degrees of freedom. The user can interactively select and position target objects for grasping. Here, the planner is used to compute collision-free manipulation motions for a model of a human arm with 7 degrees of freedom. We view this planner as a potential useful tool with applications in mobile robotics, industrial manipulators, assembly analysis, pharmaceutical drug design, and computer animation.
Fast path planning for perception-based navigation. USA.
This video demonstrates a fast path planner suitable for computing collision-free paths from navigation goals. Here's a model of a mobile robot with simulated sensors. Given a high-level navigation goal and a model of the environment, the planner can quickly compute a collision-free path to the goal without any pre-processing of the environment. Should the goal position change or the obstacles move, a new path can be computed from scratch at interactive rates. Using a simulated vision module, the robot can be made to explore an unknown environment, updating its path to the goal as new information about the environment geometry arrives. A path-following controller is used to track the computed path during the simulation. Here, the robot makes a plan based on its perceived model of the world, which is updated as new sensing information arrives. At the end of the simulation, the final trajectory traced out by the robot during exploration is shown. This planner and controller has been used to animate human character models at a high level. Here, a character is directed to navigate to a goal location in a dynamic maze environment. Cyclic motion capture data is used to animate the degrees of freedom of the human character as it follows the computed path. The planner can also be used to create collision-free following behaviors. Here, the robots are instructed to maintain a specified distance from a given human character. The goal location for the lead character is controlled interactively by the user.
Haptic applications using a virtual reality mouse. Canada.
At the University of Waterloo, our study of haptic interfaces has resulted in the development of a commercial product called the virtual reality mouse. This device is driven by 2 motors and allows a user to effectively feel the surface of the Windows environment. For example, window borders can be felt, allowing a blind user to easily find the edges of a window to resize it. The cursor can even be made to feel as if it were connected to a button by a rubber band. In conjunction with a screen reader which reads the text, some blind users have been able to be fully functional in a Windows environment in as little as an hour.
April 24 to 28, 2000 at San Francisco.
Such a blind user is Frank Fitzgerald.
It's been a great asset to me. It's actually let me, for the first time, get on the web and actually be effective on the internet and be able to actually download things and find out where I'm going and actually figure out what I'm doing.
The capabilities of the virtual reality mouse are now being exploited in other applications. Here, a 5-bar linkage manipulator is being controlled by a mouse in a teleoperation application. The 5-bar linkage manipulator can also move the mouse, demonstrating the bilateral nature of the experiment. The proposed control strategy allows the two users to shake hands. We have been able to create this force transmission without any expensive force sensors. Note that the dynamics of both manipulators are designed to have nearly linear dynamics and are backdrivable. With a small amount of feedback linearization, our control strategy can be shown to be stable for all controller gains. Here, low gains and the resulting overshoots are shown. Higher gains result in superior performance and more accurate force reflection. Another interesting research challenge involves real-time force reflection with two virtual reality mouse connected over the internet. It is desired to maintain performance in the presence of unknown time delays. Each user controls one of the cartoon characters. At the local location, the first user would see the arms move as shown. However, at the remote location, the second user would instead see the green arms due to the unknown time delays from the internet. It can be shown that, using a Kalman filter, delays of up to 0.1 seconds can be anticipated and the arm position can be predicted. Here the blue is the Kalman filter output. Notice how well it tracks the arm despite the random time delays. This implies that, using our techniques, the closed-loop systems can be made to seem as if there were no time delays in the system.
The Paradex Manipulator, a novel parallel actuated robot design for mechanical assembly applications. USA.
This video introduces a novel, parallel-actuated, kinematically redundant robot designed and built by Microdexterity Systems, Inc., in collaboration with Sandia National Laboratories. Characterization and algorithm development for this robot are being performed at Case Western Reserve University for application in assembly of Ford powertrain components. Relative to serial link manipulators, closed-chain mechanisms with parallel actuation can achieve high repeatability, high stiffness, and high payload capability. Encoders on the linear motors of this prototype have a resolution of 1/2 micron, and repeatability of the robot under controlled moves was observed to be better than 10 microns. The structural stiffness under servo control is approximately 100 newtons per millimeter. The payload of this prototype is more than 20 kilograms. Through the use of curved passive connecting links that cross over one another in space, a more uniform force and torque capacity is achieved over the workspace. A significant limitation common to parallel actuated designs is the relatively small workspace. To reduce the workspace constraints, a 7th degree of freedom is incorporated, enabling exploitation of kinematic redundancy to expand the range of reachable poses. This new robot design offers 3 additional features that are advantageous for applications to force-guided mechanical assembly. First, the moving components have relatively low inertia, permitting high acceleration responsiveness. Second, the actuators have relatively low inherent friction and are backdrivable. Third, force sensors incorporated between the actuators and the passive connecting links enable active feedback to reduce the apparent friction to negligible levels. An open architecture control system permits implementation of custom control algorithms. In particular, signals from the built-in force sensors are used under natural admittance control to program stable impedances appropriate for force-guided mechanical assembly. In these scenes, virtual springs and dampers, defined in software, guide the robot gently towards a virtual attractor. Modulation of the spring and damper parameters and trajectory control of the virtual attractor point provide a means to guide the robot through compliant manipulation for mechanical assembly applications. The unique dynamic features of this robot make it possible to modulate its mechanical impedance from highly stiff and precise behavior to unusually gentle and compliant interaction. Such capability offers promise for wide-ranging applications in automated mechanical assembly.
Flexible robot assembly using a multi-sensory approach, Germany.
This is our working cell consisting of robot, turntable, real-time vision system and 6-dimensional force torque sensor. The task to be performed is to insert all 4 pistons into the engine block, which is rotating independently at unknown speed. The system was demonstrated with great success at the Hanover Fair 99. This is the view from the hand camera. The robot is about to pick up the first piston. The image processing system is detecting the orientation of the piston in the magazine. The grasping of the piston is guarded by the force torque controller. The resulting forces are displayed in the lower left corner. The robot is approaching the observation position to estimate the yet unknown motion of the engine block. The green wireframe model visualizes the result of the vision-based 3D position estimation using a Kalman filter. When the Kalman-based position estimation has sufficiently converged, the system starts the insertion process. This time the piston jams, but the force torque controller leads the piston into its cylinder. Now the system is picking up the second piston. You can clearly see the blue compliant force torque sensor with the camera mounted to its side. Now a feature-based visual servoing algorithm is minimizing the remaining position error. The piston is smoothly inserted. Note that the robot has to keep the relative orientation during the insertion phase, due to the non-circular but elliptic shape of the pistons. To demonstrate the robustness of our system, we apply an external disturbance to the piston during the insertion phase. The connecting rod hits the cylinder rim, which triggers a reflex withdrawal movement of the robot. The second trial succeeds. We at the Institute of Robotics and System Dynamics hope that you enjoyed our demonstration.
A reconfigurable parts feeder with an array of pins, USA.
We present a method to manipulate polygonal parts using a simple device consisting of a grid of retractable pins mounted on a vertical plate. This device, which we call the pachinko machine, is intended as a parts feeder for flexible assembly. This implementation uses a vertical plexiglass surface with 23 pneumatically activated pins. We now demonstrate 2 automatically generated plans. When the part is dropped from above, it is captured only when in a certain set of initial configurations. The part is manipulated by dropping it through a sequence of activated pins. This second sequence, also generated using configuration space representation, has a different start configuration but reaches the same goal configuration. The remaining sequences shown were manually generated. Here the part reaches the same goal configuration from a different initial configuration. Parts in undesired orientations can be ejected for recirculation. The remaining examples demonstrate the pachinko machine manipulating different objects. Our future plans include adding more pins and using infrared sensors to distinguish and sort parts.
Prototype pallet handling device, USA.
A robotic system is under development for autonomous loading of pallets into cargo truck trailers from loading docks. Stewart Glapat Corporation holds a patent for this pallet handling device. The goal is to reduce shipping costs in industries with high cargo rates and uniform pallets. The focus of this work is to develop and implement the autonomous controller. This video demonstrates prototype hardware developed by Ohio University. A 1/8 scale prototype with 5 axes has been designed, built, programmed, and tested. An existing conveyor system will be modified to provide pallets automatically to the robot forks. This system is not in the prototype. The control system is based on a programmable logic controller. Ladder logic is used for sensor-based programming. The sensors include infrared and ultrasonic sensors for distance feedback and limit switches for presence detection. The system is designed to operate autonomously via sensor feedback. A manual mode is also enabled for error recovery. Prior to autonomous loading, the unloaded robot enters the trailer to measure the cargo space. The robot returns to pick up the first pallet. This pallet is then deposited in the proper location. The robot returns to pick up the next pallet. This procedure repeats until the last pallet is loaded. The robot has 5 degrees of freedom, 4 prismatic joints, and 1 rotary joint. A passive freedom is included for unloading the pallets from the forks. This demonstration loads 3 rows of 2 pallets. The system can handle up to 11 rows of 2 pallets for full-size trailers. The prototype hardware has yielded many design lessons which will be incorporated in the full-scale system. The prototype has demonstrated that the pallet handling device is feasible. The autonomous control succeeds even with errors such as trailer misalignment and height uncertainty. The goal is to allow high-throughput cargo loading with minimal human involvement. This work will be extended to development of a full-scale prototype and evaluation of the system at a working loading dock. Ohio University gratefully acknowledges financial support for this project from Stewart Glapat Corporation.
Sensor-based motion planning for manipulator arms, an eye-in-hand system. Canada.
The Robotics Lab at Simon Fraser University has developed a general-purpose, sensor-based motion planning system for articulated robots with many degrees of freedom. It enables a robot to move to a desired goal, sensing and planning as it moves in unknown static environments, avoiding collisions with obstacles. The hardware consists of a 6-degree of freedom Puma robot with a range sensor mounted at its wrist. It consists of a laser striper that scans across the scene to obtain a range image. The robot builds and updates the internal representations, modeled as octrees, of the physical obstacles and the free space as each scan is taken. Our planning framework is roadmap-based. A roadmap is a finite graph structure in configuration space, with each node representing a free robot configuration. The yellow dots are unknown robot configuration. That is, they would result in overlap with unknown physical space. Green dots represent the free nodes in the roadmap. Red dots are forbidden robot configurations. That is, they'd result in collision with obstacles. A green line between 2 nodes indicates a free path between the 2 corresponding configurations. The crux of our approach is to incrementally build a roadmap as the sensor senses parts of the environment. Think of this expansion process as a wavefront of known, free configuration space expanding toward the goal. A key idea in this incremental approach is the concept of yellow nodes. Here, the robot task is to reach a goal configuration that goes under the white pipe. The initial configuration of the robot is vertically upwards. In the CAD model, a small vertical cuboid around the initial robot configuration is assumed to be free. The region outside the cuboid is completely unknown. The fundamental unit in the planning process consists of a move followed by a scan. Each scan is used to update the Octree world model and to further expand the roadmap in configuration space. Here's the final roadmap. Here, the robot took 9 scans before finding a collision-free path to the goal in about 20 minutes. The eye-in-hand system developed at the SFU Robotics Lab is a key step towards autonomous exploration of unknown static environments and has applications in several domains, from space stations to hazardous waste removal in nuclear reactors.